Okay, so before we start, let me give you some announcements, no? So the requested face-to-face schedule on Wednesday, 10:30 to 11:30 has been approved by the chairman. So we will meet at room 168. 168. So Wednesday will be our schedule for face-to-face meeting, no? Instead of our official schedule, which is 3:30 to 4:30, so we can meet 10:30 to 11:30 as requested. Then the room number is 1680. So is that clear?
Will that be every week pa, sir?
Oh, every week. We should have at least one face-to-face meeting every week.
Sige, sir. Thank you,
So,
sir.
may kuan? Nay mga kuan? Because the information I got is that everybody is amenable to that schedule. So is that correct? No objections? 10:30 to 11:30? And so that would be official, no? So wala na siyang atong schedule. So we start with this schedule by next week, no? So 10:30 to 11:30 every Wednesday. Then another announcement. What? Sige. We will meet this Friday face to face, no? Kaya kanang Wednesday nga face to face that would start next week. So karong Friday meet na because I will be distributing to you the lecture materials, no? So it is important that you have already a copy of the lecture notes this week. So ano siya purpose sa atong meeting karong Friday, no? Aron masugdan na nato distribute ang lecture materials. So bring your payment, 200 pesos for each copy. So karong Friday, mumita at the same schedule, no? Katong 3:30 to 4:30. So okay rin? Ito na ba may question regarding those announcements? So if there is none, let us continue now with our lesson. No? So let me share to you my screen. Siya naman ito share screen. Ano yan? Okay, so makita na ang kuhan, gi-share na akong screen.
Yes, sir.
So this is the first type of footing that we're going to discuss, no? That is the spread footing, also called isolated footing, and square footing. No? So those are different names of this type of footing. So it is called a spread footing because its purpose will be to spread the column load to the soil, and this is also called the single column footing, no? Because it supports only a single column. So let me discuss this example. So in the problem, design a spread footing for a column 600 millimeter by 600 millimeter in section to carry a dead load of 1,850 kilonewton, a live load of 1,150 kilonewton. So assume the allowable soil pressure and service load to be 260 kilopascals. Somebody is still trying to join. Okay. Then use F sub C prime 20.7 and Fy 276 megapascal. So from the statement of the problem, it shows us the necessary information that we need, no, before we can design the footing. So the footing is one of the last structural element that we're going to calculate if we are designing, for example, a building, no? So inigabot na to sa footing design, ang presumption na nga nahuman na itong design sa superstructure. So nahuman na itong design ang slab, ang beams, ang girders, ang columns, no? Sa musod, nahuwahin mo kanya sila mga bot. Ako ba'y sod? Ano? Anong ni... Ano to? Okay. So, ang presumption ini nga nahuman na natong design ang superstructure, nahuman na natong design ang column, no? So, kung nahuman na design ang column, nahibaw na tag pilay load nga gikari na ng column. And of course, that load supported by the column will be the same load supported by the footing, no? So, mo nang natay dead load, live load. Now, in this example, we will consider first when the loading is pure action loading. So wala pa tayo bending, no? Ni kaduhang kuan kinahanglan kay bawo na ta sa allowable soil bearing capacity. So that data is obtained from geotechnical investigation, which is usually done by a separate consultant, no, the geotechnical engineer. So kuha na nagikan sa geotechnical report. For example, I will show you maybe this is a hard copy, no? So I will just bring this coming Friday so you can see how a geotechnical report looks like. So gikan na ng report, makuha na to ng information regarding the soil bearing capacity. Then regarding the material strength, so concrete to steel, kita mo decide ni ana, no, as the structural design engineer, kita mo specify pila may strength sa concrete o sa steel nga itong gamiton. Of course, selection of the strength of concrete and the strength of steel. Well, sa strength sa steel, di man kayo dagdag option, no? Duhar man ang common grade sa steel diri sa Pilipinas. We have grade 40, which is 276 megapascal, and we have grade 60, which is 414 megapascal. So kung mga light ra nga mga application, residential buildings, then we can use grade 40, but for high-rise building, we usually use the higher grade, grade 60, no? And for concrete, so natay 3,000, probably the lowest, no, structural strength of concrete that is commonly used. So 3,000, 4,000, 5,000, 6,000, 7,000. So usually concrete strength is specified in increments of 1,000 PSI, no? Or in megapascal, so in increments of 7 megapascal. So we have 21, 28, 35, 42 megapascal, and so on. Okay, so muna siya ang mga preliminary nga data na kinahanglan nga itong i-gather na moabot sa pag-design sa footing. So I've shown here a step-by-step solution. So in step 1, we proportion the footing dimension based on service load condition. So we compute the total column load, which is the sum of the dead load and the live load. And since the soil is to support the column load and the weight of the footing, no, so we need to estimate the weight of the footing. Uh, and since we do not know yet the footing size, no, kabaw size footing ang atong buhaton na mo assume lang tayo certain maybe you can assume a size, then from that assumed size you compute the weight, or usually it is easier to assume the weight of the footing to be a certain percentage of the column load. So for spread footing, the weight of the footing usually ranges from 8% to 12%, no, of the column load. So for simplicity in our calculation, let us just assume 10%. No? 10% of the column load, we get the assumed weight of 300 kilonewton. So the total load supported by the soil is the sum of the column load plus the assumed weight of the footing. Then next we compute the required footing area. So this is just a variation of the simple stress formula. You have the stress is equal to the load divided by the area, no? And solve for the area, we get the load divided by the allowable stress. So in this case, the load is the combined load, no, of the column plus the weight of the footing, and the stress is the allowable bearing pressure. No? Then if we are designing a square footing, then the dimension of the footing will be equal to the square root of the area, 3.56. Then usually ini siyang dimension kay di man exact ato ni siyang i-round off, no, ngadto sa mas practical nga value. Usually an increments of 0.1 meter, no? Ano siya common increment sa kining footing dimension. So ang 3.56 atong ground off ngadto sa 3.6 by 3.6 meter. Then once we compute the actual area of the footing and compute the factored column load. So this time we multiply the load by their load factors. So in this solution, the load factor for dead load is 1.4, for live load 1.7. But based on the NSCP 2015, no, NSCP 2015, when dead load and live load combines, the load factor for dead load is 1.2, and the load factor for live load is 1.6, no? So if you use the NSCP 2015, it should be the calculations, no? Times 1150, okay? So, na siya ay changes siguro nga kinahanglan nga atong bantayan. So just take note of that, no? Because in the plates, we will use the NSCP 2015, no? Yung mga load factors. So after this, we compute the net ultimate upward pressure. We divide the factored column load by the actual area of the footing. So take note that in computing the factored load, we don't include the weight of the footing, no? Because if we were having class face to face, I would have asked you that question. But since this is online lecture, I'll just tell you why, no? So kung ang atong tanaw na ang action, no? Ang effects sa weight of the footing. So the weight of the footing is distributed over the footing, no? So kay downward nga distributed load, and it will be resisted by an upward distributed nga soil bearing pressure. And since the two pressures, one downward, the other upward, no? So they will be linear and opposite, the same magnitude, so they will just cancel out, no? So there will be no shear and moment induced in the footing slab due to the weight of the footing itself, no? That's the reason why in designing the footing slab, no, we don't consider the weight of the footing, no? We consider only the weight of the footing in computing the required footing area. So pag nagpadayon siguro join, na ni gawas. Murag na may okay. So by the way, feel free to interrupt if you have some questions. So from step one, we already have the required area of the footing. No? So the next step will be to determine the depth, the effective depth of the footing. And from the effective depth, we add the protective cover. Then we'll get the required thickness of the footing. Now, the thickness of the footing is usually governed by shear requirement. No? So, mo nang ato ni siyang i-compute based on shear requirement. And there are two kinds of shear here. We have the wide beam shear and the punching shear. So, sa wide beam shear nga failure, so ingon ini, no? Na siya nga atong illustration. So, upward pressure dire, the critical section for wide beam shear, according to the code, is computed at the distance from the face of the column. So kaning atong footing will behave as a cantilever, no, projecting from the face of the column. Ini siya cantilever diha. Then the critical section at the distance, no. Okay, so we just compute what is the shear force acting at this critical section. And evidently that would be the upward pressure multiplied by this tributary area. So we have here the calculation for the factor shear. So that is the net upward pressure times the tributary area, which is 3.6 times this dimension 1.5 minus d. So here we express the shear in terms of the unknown effective depth d. Then next we compute the shear strength or shear capacity, no, which is given by the formula phi 16 square root f sub c prime bd. So we substitute, no, f sub c prime, ang b is the width of the critical section, kani siya, dimension. Yang kani siyang 1,000 is to express, no, kay kani siyang atong kani siyang quantity nga phi 16 square root f sub c prime, this is in megapascal, multiplied that, so you should multiply this by millimeter to obtain Newton, no? Diba? But convert to kilonewton, no? So kaning B, so nakay kining BD nga MMMM, no? So convert to meters, that is 10 to the 6, but you convert to Newton to kilonewton, so you divide by 1,000, no? So the net conversion factor will be 1,000. Now, for adequacy, the shear force should be less than or equal to the shear capacity, no? So yeah, then you equate, and you'll get an equation which involves only the effective depth as known. You can solve that, no? So this is the depth required for beam shear. Now, the second condition is the requirement for punching shear. So if the footing is too thin, then there is a tendency for the column to punch a hole through the footing, no? And the critical section for beam shear, according to the code, may be computed at d over 2 distance from the face of the column, no? So d over 2 dire, so that makes total of d, no? So if the column dimension is 0.6, then the dimension of the critical section for punching shear will be 0.6 plus d. Okay, so we follow a similar calculation. So we compute the factor shear, that will be the upward pressure multiplied by this shaded area, which is the tributary area. So that is simply the area of the big square minus the area of the small square. Then for the shear capacity for punching, no, sa beam shear 1/6 man to, no, sa punching it is 1/3. So we have 1/3 square root of sub c prime. Then BO is the perimeter of the critical section. So the BOD is the resisting area, no? Okay, so we have here the perimeter is 4 times the length of the side, no? So 4 times 0.6 plus d multiplied by the effective depth here, no? And we have the conversion factor of 1,000, and we equate, no, the shear strength to the shear capacity. Then we'll get an equation which is in quadratic, no, in terms of d. course, you can easily solve that by using the quadratic formula, and we get this answer. So from step 2, the required effective depth should at least be 0.529 meter for punching 0.632. So evidently, to satisfy both requirement, the larger value will govern. No? Kaning 0.632, ato na siyang i-run off to a practical value. We usually increment so 50 mm, no? So 632, we say use the of 650 mm. If like cover, so 650 plus 75 or sometimes 100, no? So you have a TMM fit. So the next step will be to compute the steel reinforcement. So the action of the upward pressure is that it will tend to bend the footing upward, no? So if the footing is bent upward, so we can see the tension, of course, at the bottom, compression at the top. So we place the reinforcing bars at the bottom, no? Which is the tension zone. So ang atong critical section for bending, mura man ni siya cantilever, no? So ato yung nari siya fixed dire, no? Then free towards the edge of the footing. So we compute the bending moment at this critical section. So you have upward pressure multiplied by this area, you get the resultant force multiplied by its moment arm, which is half of this distance, no? Half of 1.5. Kaya kana siya nga resultant force will be acting at the centroid, no, of this tributary area. Yun ang mag-act ang iyang resultant, no? So ang iyang moment arm is 1/2 o 1.5. So you see, no, na kining mga calculation, there is really not much of a difficult analysis here. No, all we have to do is to apply what we have learned sa engineering mechanics for determining resultants, strength of materials for stresses, and of course allow stresses gikan sa concrete design, no, which are usually empirical, no. So mao ni siya calculation nato sa factor moment. 350 is the net of upward pressure, no? Then 1.5 times 3.6, that is the tributary area. Then 0.75 is the moment arm, no? So pressure times area gives you force, multiplied by moment arm gives you moment. So once you have the factored moment or the design moment, then we can apply what we have learned in reinforced concrete design to compute for the steel area, no? Maybe some of you have not yet taken up reinforced concrete. These are the formulas that we need to apply, no? Why kaning design is straightforward sad, no? Why dagang liko-liko. So given ka sa moment, ano yung mga formula nga itong gamiton, no? So I will not explain anymore how these formulas came about. That is part sa reinforced concrete design nga subject. So we compute RU using the formula MU over VBD square. So we already have here all the necessary data we need. So we obtain RU, compute the strength ratio M, which is Fy over 0.85 F sub C prime. Then compute the required steel ratio, no? Using this formula. So we have already the value of M, the value of RU, the value of Fy. So we can compute for rho. And we check that against the minimum steel ratio required by the code, no, which is given by this equation here, no. So 0.25 square root of C prime over Fy, not less than 1.4 Fy. So kini siyang 0.25, magawas nga 0.00412, 1.4 over 276, gawas nga 0.00507. So between ining duha, ang mo-govern is 0.00507, no, with rho minimum. And compare this with the required steel reinforcement ratio. So there are two possibilities here, no? Let's copy this one here. So when rho, I don't have here rho, so I'll just write P. Okay. So when rho required is greater than rho min, no, or greater than or equal to rho min, use of course rho required, no. So kung siya mo ring rho required, no. So it is also possible nga ang atong rho required is less than rho min, no. So may atong dire. So the code says that we may use, no, so you may use the smaller, no, smaller between 4/3 row, 4/3 P required, and row min. So muna siya netabo dire, no, kaya atong row required is only 0.00388, row min is 507, so row required less than row min. So we compute 4/3 of row required, no? So which gives us 0.00517. May siyang value na gamito na to ang gamay, mas gamay ni ini o ni ini. So 0.00507. So once we have the steel reinforcement ratio, then we multiply that by BD. No? We get the steel area. Then select the bar diameter and compute the area of the bar. And next we can compute the required number of bars. Simply divide the total area required by the area of one bar. Pag divide na to, di mo na exact, so we round off to usually to the next higher integer. No? So kung 24.2, then we say use 25 pieces of 25 mm diameter bars. Now, since this is a square footing, carrying pure axial loading, then the forces will be symmetrical. No? So whatever reinforcement we need in the x direction, it will be the same amount of reinforcement we place in the y direction. Okay? So muna may ingon both ways. Both ways. And we check the spacing of the bars. So we just verify whether the bars are not too far apart or too close to each other. No. So this is the formula for the clear spacing between the bars. So width of the footing minus 2 times the cover. 2 because we have cover on each side. And NDB, that is the space occupied by the bars. And divided by N minus 1, this is the number of spaces between the bars. No? So substituting the values, assuming a cover of 75 mm on each side, we have 25 of 25 mm diameter bar, and we get a clear spacing between bars of 117 millimeters. Now, usually the desirable spacing is between 75 to 200, so this is 117, therefore that's okay. Now, of course, this is not an absolute requirement, no, that is just as stated there, desirable. No? Sometimes you can go to 50, 300, no? But that is a desirable spacing, maximum 200, no? Pero wala din na. It is a matter of judgment, no? But this is just a guide. Okay, next we check for the development length, no? So the purpose of development length, if we consider here, no? Muna siya nga itong footing, another in column, and this is your critical section here, no? For bending. Yang imo reinforcing bars, tangin mo diyan, no? Okay, so if we pass this section here, then isolate the left or the right free body diagram. So yung una then we have here the tension, no? The tension in the reinforcing bars. So for the bars to develop its full tensile strength, it should have sufficient embedment, no? Kung buo na siya globong, it will be pulled out. Okay? So atong i-check karon pila may kuan, no? O makapasa ba ni siya sa required nga embedment length or also called development length, no? So ang formula na to sa development length mo ni siya kaning formula, no? This is given by the code. There might be some minor changes of this equation in NSCP 2015, no? Just try to clarify that when we meet face to face, I will bring a copy of the code, no? Wala siya nga formula, ang minimum kini siya. Mura ng tulong may atong tanahon, no? Okay, kini nga formula o minimum, no? So naa kay mga kuan diha, mga factors, no? Alpha, beta, ang sanang y na how do we read that? Lambda. Sometimes I am confused reading these Greek nga mga letters, no? So kani siya tawgon ta ni y, kani siya I think this is how do you call this? Lambda ni siya, kani siya unsa man ni? Epsilon. Okay. So you have the size factor, the coating factor. So these are actually defined, no? Sa ano, I think we have some definitions here. Sure. Any other? Or a development length factor. So alpha, that is the reinforcement location factor. So the value is 1.3 if top bar, 1.0 for other reinforcement. So what top bar is defined as a bar which has more than 300 millimeter of concrete below it, no? So muna siyang gitawag na ito nga top bars. Okay? Kanya that is the coating factor. So of course if you coat the reinforcement, ang iyang bond, no, to concrete will be lessened. Kaya mo dangog naman ang surface, no? The surface of the bar becomes more slippery, no? Kung naa siya ay epoxy coating. So purpose of epoxy coating the bar is to protect it from corrosion. So these are usually applied if you are building near seawater, no? Outdoor, no? Where bars might be prone to corrosion. Then kanang Y, that is the reinforcement size factor. So 0.8 for 20 mm diameter and smaller, 1.0 for 25 mm diameter and larger. Then lambda, that is the lightweight aggregate factor. So 1.3 when lightweight aggregate concrete is used. But usually we use normal weight, no, aggregate. So 1.0 for normal weight concrete. Okay, so kani siyang KTR, well, we don't have to worry about that because that is usually applied when we design beams. So muna siya diri ang mga factors na to, no? Okay, so based on the first equation, LD over DB is 26.1. In the simplified formula, LD over DB gives us 43.68. So mas dako nining duha may mo-govern. So kaning 43.68 and to solve for LD, so kaning DB atong i-multiply diri sa 43.68, no? So we get 1,092, minimum of 300. So between kaning required ug kaning minimum, so kini siya nga value mo imo govern, no? So kung natong tanawon kung we have sufficient embedment, no? So ang atong embedment sa atong bars is gikan sa critical section towards the end of the bar, no? So we check in the distance if this is greater than the required embedment length, no? So from the critical section to the edge of the footing, the distance is 1,500, no? You subtract the protective cover, which is about 75 millimeter. So you still have 1,425 millimeter of embedment, no, which satisfies the required development length. No? So therefore, this is okay regarding the embedment length. No? So there is no need for providing end hook here. No? Now, in case nga kani siyang atong LD provided is less than LD required, then we can provide end hook, no, to increase the anchorage. So dili kinahanglan sa tanang higayon nga butangan natong end hook, no? End hook can be 90-degree nga hook, it can be 180-degree nga hook. Depende ra na, but it is common to have 90-degree hook. It is easier to fabricate, but it will require a longer extension length, no, than the 180-degree hook. So in terms of amount of steel, mas economical ang 180-degree hook kaysa 90-degree. But in terms of labor, sa yun buhaton ang 90 versus 180, no? Pero karon maana mo yung mga rebar bending machine, dali na lang bisan pag mag-bend kag 180-degree, 25 mm diameter, that can easily be bent, no? So mas maayo 180-degree na lang, no, to save on steel. Kaysa labor, di naman kayo matter kung gamit kag makina, no? Ay makina, kusgan mo na makina, di pareha mo na mano ba, no? Hago kayo. Okay, so step 5, this is on dowel requirement, which is usually not a concern, no? Kay ang atong common practice, ang tanan nga rebar sa column, we embed it into the footing, no? So mo na nga sa detail na to. Ingon ni nga atong sitwasyon, no? If the column rebar, example, let's draw a column rebar here. So ang column rebar ka na, then we provide at the lower end of the bar, a 90-degree bend, no? So that the bar can sit on the footing rebars. So kung ingon na atong plastada, then there is no need to compute sa mga dowel bars. Okay? Hindi na natin i-discuss katong sa dowel nga portion. Now, kini siya dire, no, sa step 6 atong gi-check ang weight sa footing, because as you recall here, no, the start we just assumed the weight of the footing be 10%, no, but now we have the size of the footing, so we can check the actual weight. So ang atong thickness will be the effective depth plus the cover of 100, no. Again, this can be 75, so we get 750 mm. And the volume of the footing, 3.6 by 3.6 times 0.75, we get 9.75, no? Or 72 cubic meter. So multiply that by the unit weight of concrete, which is 23.5, 23.56, or sometimes 23.6, no? It doesn't matter. Those are minor differences. We get a weight of 229 kilonewton. So i-compare na mo nga rin sa itong assumed weight na 300, actual weight is less than the assumed weight, so therefore okay. And of course, you can still improve, no? Probably you can go back, okay, medyo layo mo sa kayo 300 ang atong gi-assume, yung actual weight 229 ready ay. So it means that the size of the footing is a little bit oversized, no? So pwede kong mubalik na to sa step 1, no? Imong pagamyan ang imong assumed weight. So you perform an iteration, no? So when you have this calculation implemented in Excel, then that would not be a problem, no? Because you can just iterate easily. No? Pero kini siya, no, basta di lang kay dako og diferensya, then usually second iteration is not necessary, no? Considering that for example, kining atong allowable soil bearing capacity nga 150, kaning gihatag diri nga 260 kilopascal, this is just a more or less value also, no? A factor of safety nini nga 3, sometimes 4, no? So dili kinahanglan nga accurate ko kay ka to the nearest centavo ba, no? Ano man. So mga naitimanan na to kining design labi na sa mga foundation so, na mga values diri nga dako siya uncertainty. Bisan kani mga loading na to 1850, 1150 di man ni siya kuan gyud eksakto no estimated naman na siya nga loading no. Di man na siya parihag kasa prinda kag alahas nga timbangon gyud pilay weight sa imong necklace no. Hindi man ingon ana. So the mga assumption na to, mga approximation are within no a reasonable degree of accuracy sa atong desired nga results. So we don't need to be overly accurate no because we really can do that no. So yun na. Then of course kini siya humanining atong mga computation we have to translate them into design drawings. Ang mga foreman di man sila interesado ni imong beam shear, punching shear, unsa day mga aryo nimo no. Dili man na mo ilang kuan, ilang masabtan ang drawing. So ang guide lang ni mga drawing no is that you try to imagine no what information do you need no in order to construct the footing. Tanan nga information imo nang translate mo na sa drawing no. Hindi kay kuwang-kuwang. Ang drawing gani kinahanglan ayuhon atong drawing no. Mata mga section di man ta grade 1 section 11 di ba? Tapit naman ta mo graduate, tapit ta ma-engineer. So, we have to produce a drawing worthy of an engineer no. So ayan na yung kanabitang trabaho nga murabag di wala lang kanang minimal effort no. You try to exert more effort, best effort no as much as possible. Unlike students who just exert minimal effort no. Basta lang makasubmit di makita nimo nga murag naagi paningkamutan gyud gitarong mayo no. Your handwriting should be improved. Okay? Now, ngari sa previous discussion, no? Dire, so for punching shear, ato rang gikuan kini nga formula, no? Print screen. Image. Kini siya nga formula mo atong gigamit, no? Actually, naapay laing duha ka formula nga nga i-check, no? So, kawas na ini, i-check sa nato ning formula 411-35, 411-36. Pero kasagaran gud kay bina kung interior nga column kani man siya nga kuan mo im govern, no? But anyway, it is good to know there are still these two formulas which needs to be verified, no? Kaning formula beta C define na the ratio of the long side to the short side of the footing, no? So kung square footing, then ratio of the sides will be equal to 1. Nya kaning alpha S depende kung asa na locate no ang imong column relative to the footing. So kung mo ang footing mo ni siya atong column. So kung the column is at the center no then alpha S is 40. If the column is at the edge of the footing that's 30. Then if the column is located at the corner of the footing that's 20 no. A corner column. So ino lang na no. Kaya alpha S, BOD, beta C. So, kani siyang coefficient rin, makita na to ng mga coefficient. Kani siyang coefficient. Kani siyang coefficient. So, mo siya tumbas-tumbasan na ini nga coefficient. Kaning 1/3, no? Parang mo sa 1/3, no? So, asay mas dako niya na, o ang gamay no ang gamay kay this is capacity so ang gamay mo atong mo govern no Okay, so that's it for this meeting. So I hope that you will attend no, this coming Friday. Aron kadawat sa mga kopya sa inyong lecture materials. So, balik ta. So, doon na ba yung mga pangutana? Na to today's chat, no? Kasi na mo yung mga question. Pwede less than 10%. Pwede, no? Pwede less than 10%. Kaya ka na assume mo maguna, no? Assume gani, then your guess is as good as mine, no? So ay, ka-timing ka, imong assume dool dahil tinuod, o sa sa layos tinuod. So kung dool tinuod, okay, hindi pa ita, og layos tinuod, hala, revise, no? Second trial. Ano ba na, no? Kanya karon nga na Excel, so dali na lang kayo i-change. No? So, do you have any questions aside from this one? No. So, ang gamit og dowel. Sa ako nang gikaingon, ang common practice god ang column rebar ilubong magina dito sa footing, so no need for computing dowel bars. Yung dowel pwede na siya kuhan kung mga precast kay column niya o na kay footing kasi in place, then you have a precast na column. Then of course you have to connect the column to the footing, no? That's the purpose of the dowels. Provide connection between two concrete elements, no? Usually sa precast na construction. Do you have any other questions? What about the others? So we will try to meet at least once a week, no? And that is the time that I will discuss, no? The inline yung mga footing design. Really prefer face-to-face na class, no? Rather than kaning online. Online, very little interaction. I cannot even see your faces, no? Sana mo diyan, ipahiyong na ba mo, imugot na ba mo, naon na, no? Okay. So, unsa man, kinata? The next class will follow, no? Duha man ka section kasunod, 3:30 to 4:30, then followed by 4:30 to 5:30. So maybe the other section is already waiting, no? Okay, ito kadugay karon. Sige, ayaw mo diha.
Thank you, sir.
Bye, sir.
Okay.